Last time we talked about objects rotating, and we found, that this rotation, we could characterize it as 1D motion where that dimension is angle. So we had angular displacement, angular velocity, angular acceleration, and it ends up being just like the 1D motion that we started out with in the beginning, along an x-axis. So what I want to talk about today is rotational kinetic energy. So imagine a disk, let's say it's a solid disk, and it's rotating at some angular velocity omega about a central axis. So we already discussed that each one of the little points on this disk is rotating at a different tangential velocity. And we have an expression for kinetic energy of an object, just a point mass or center of mass of an object, 1/2 mv squared. But in the case of a rigid object under rotation, all of those velocities are different. If you're breaking it up into little bits of mass, let's say I'll call this M1, it's traveling at some V1, and over here maybe it's a little closer to the axis of rotation. This is V2, this is M2. So to find the kinetic energy of this object, it definitely has some kinetic energy. All these particles are in motion. You have to sum up over all these little bits of mass and all their velocities squared. So I can write that down. The kinetic energy is approximately equal to the sum over I. Maybe I should sum over, it doesn't matter. I'll sum over I. The sum over I of 1/2 m sub I v sub I squared. Right? In this case, the way I've done it, that would be, m1 v1 squared, or 1/2 m1 v1 squared, 1/2 m2 v2 squared, and I sum over all those little bits. Okay? So imagine breaking this up into little bitty bits and all their little velocities. But we know from what we did the other day that we have an expression for the tangential velocity of all these little particles based on the angular velocity. If this M1 is at some distance R1 and M2 is at some distance R2, okay, for each little individual V sub I, that's going to be R sub I, not M sub I, that's going to be R sub I omega, right? That's just the radius, that's the distance from the axis of rotation times the angular velocity. That gives you that tangential velocity. If it's farther away from the axis, it's going faster. If it's closer, it's going slower. Because all the objects, this is a rigid object, all the objects are rotating at the same angular velocity. So I'm going to use this and plug it in here. So kinetic energy, I'll just put equals. Pull the 1/2 out front. 1/2 times the sum over I of m sub I, R sub I, omega squared. Just substituting that in for V sub I. Now, I'll square this out. This is equal to 1/2 times the sum over I of m sub I r sub I squared omega squared. All right? We give this quantity, that sum over I of m sub I r sub I squared, we give that quantity a special name. That's called the moment of inertia. This moment of inertia is the rotational equivalent of mass. So typically given the letter I, remember when I was talking about impulse, I use the letter I, and I think I mentioned something about, I don't use it often for impulse because typically we use it for moment of inertia. This is moment of inertia. It's just a name, but okay, that's what everybody calls it. Moment of inertia is the sum over I of m sub I r sub I squared. That's for a bunch of little point masses. So if you have a bunch of little point masses, they're rigidly fixed to some axis of rotation. If you want to know the moment of inertia, you sum it up. This is very similar to center of mass, because for center of mass, we had the mass times the position. For moment of inertia, it's the mass times the position squared. So this moment of inertia not only depends on the mass of the object, it depends on how the mass is distributed. If the mass is farther away from the axis of rotation, this moment of inertia goes like r squared. You're going to get a larger moment of inertia rather than the mass being closer to the axis of rotation. If you've ever tried to rotate like a big heavy wheel that has mass that's on the outer rim of the wheel, very hard to rotate to get it started. If the mass is concentrated more at the center, it's easier to get it started. Okay? I wish we were able to do the labs, because in lab we do this moment of inertia procedure and you see all this stuff in action, but unfortunately we're not able to do that. So, okay. So for continuous objects like disks and spheres, spherical shells, thin rods rotating, all these kinds of things. For a continuous object, and I'm not going to go through the math, but you break it up into smaller and smaller pieces. You take the limit as little m goes to 0, or maybe you call it delta m, or you take the limit as I goes to infinity, and the moment of inertia is equal to the integral of r squared dm. So you break it up into little bits of dm, you're summing over all the little masses times their position squared. Okay? So let's look at just a simple case, very simple case of a point mass, or 2 point masses. Let's say you have a shape like a dumbbell. Here's a mass on this end and a mass on this end, and this, you want to know, that's pretty good. You want to know the moment of inertia about this axis of rotation. Call it r from that position. So this is a distance r from the axis of rotation, and this is a distance r from the axis of rotation. So where you're choosing the axis of rotation will also change the moment of inertia. Objects have different moments about different axes. In this case, I is just equal to, I'll write it as that summation. Okay? It's equal to m r squared plus m r squared. I sum over the mass times the square of its location, or its distance from the axis of rotation. So this is 2mr squared. That's simple. For point masses, you add them up. Something like a disk, when I say a disk, I mean a solid object. Here's a disk. This distance, call it capital R, and let's say that it has a total mass m. So the mass is evenly distributed throughout the disk. This has a moment of inertia, we're not going to derive it, of mr squared over 2. For a ring, or a hoop, where all the mass is concentrated at the edge, okay? So take all this mass that was contained in the disk, so here's a ring, call it a ring or a hoop. Take all this mass that was evenly distributed in the disk and concentrate it out here at the edges. So this has total mass m, and it has the same radius, but the mass is distributed differently. This, for the ring, the moment of inertia is mr squared. Okay? If we had time, we could calculate some of these. I could show you how to do the integrals and calculate these moments of inertia. Very similar to calculating the moment of inertia the center of mass. You're summing over the object, you're breaking it up in little bits, but instead of a mass times a position, you have a mass times a position squared. For a thin rod, so for a thin rod, say it's a little cylinder, very thin, has length L, and you're looking at the moment of inertia about the center of the rod. I is equal to mL squared over 12. Okay. That's just the way it works out. If we had time, I would show you how to calculate this, but we don't. Moment of inertia has units of kilogram meters squared or gram centimeters squared. It depends, just like anything else. Standard units are kilogram meters squared. Okay? So for all of these rotations, the moment of inertia plays the role of mass. Kinetic energy for translation, we already know, is 1/2 mv squared. That's the mass times the velocity squared. We derived that. Okay, you've used it several times. Kinetic energy for rotation, I wrote it down a minute ago. That is equal to 1/2 I omega squared. Okay, that summation over all the little point masses went into this moment of inertia, and then you have the angular velocity squared. Okay? So let's calculate the kinetic energy for a regular object like a disk. As a matter of fact, I'll use a disk. Here's a disk. It has a radius of 0.5 meters. That's a pretty big disk. That's a meter-sized disk. Let's say that it has a mass of 0.5 kilograms, so not very heavy, about a pound, 1.1 pounds. So very lightweight, big disc. The mass is evenly distributed. Okay. I'll give it a reasonable angular velocity. Omega is equal to 2 radians per second. So that's its angular velocity. Let's say it's rotating this way. Doesn't really matter. And you want to calculate the kinetic energy of this object. Well, you just plug it in. However, you have to know the moment. You have to know, is it a disc? Is it a ring? Is it a sphere? Is it a spherical shell? Whatever it is. Okay, so in this case, I said it was a disc. So I is equal to mr squared over 2. Okay? So I'm going to plug in the numbers. Kinetic energy is equal to 1/2 times that moment of inertia, which is, don't think my brackets are big enough, which is 0.5 kilograms times r squared. R is 0.5 meters. This is getting ugly. .5 meters squared. And then what else do we have? Omega squared. Omega is 2 radians per second. And I left out something. I need a 2 here. Because for the disk, it's mr squared over 2. Okay? I think this is pretty simple. I've got a half, that's 2 squared, that cancels out. So I have 1/2 times 1/4, which is 1/8. So this is equal to 0.125. Can't draw a J. Joules. All right. Not a whole lot of kinetic energy, a little bit. This is it, 1/2 I omega squared. This plays the role of the mass, this plays the role of the velocity. It is a velocity. It's angular velocity. Okay. So, we have the idea of energy or kinetic energy for an object that's rotating. I want to look at some calculations with torque. So we talked about torque briefly in the lab before everything happened and we all had to go shelter in place and all that stuff. So recall torque if you can. Torque is this idea of a force acting at a distance. So you have what I call a lever arm or a moment arm. If you're an engineer, you call it moment. If you're a physicist, you call it torque. Just like opening a door. Okay, you're applying a force. There's an axis. I'm pointing at a door. You can't see it, but there's an axis of rotation. The hinges. You apply that force, and you're rotating the door open. Torques tend to rotate objects. So you're applying a force at a distance, and that's causing a torque about that axis of rotation. So you have the position vector, r, and some force vector acting out here at this distance, this moment arm or lever arm. And then there's an angle between the two, and I'll call it phi. So the angle is between R and F. You know, if you moved F back here, that would be phi would be that same angle. Counterclockwise torques, if you don't remember, typically make those positive for clockwise torques. You make those negative. Just like you do with the unit circle. When you're measuring angle, you're measuring from the positive x-axis. That's a positive bit of angle. Okay, so a counterclockwise torque is positive. It is a vector. You put your fingers in the direction of the torque, and your thumb gives you the direction. You put your fingers in the direction of the intended rotation, and your thumb gives you the direction of the torque. To calculate the torque, it is R. We usually use tau for torque. It is R cross F. So maybe next time on Monday, I know we've got like, one day of class, official class left. On Monday, I'll talk more about the cross product. But this cross product is a vector product. Its magnitude is equal to magnitude R, magnitude F, times the sine of phi. When we talked about the dot product or the scalar product, meaning that when you take the dot product or the scalar product, you get a scalar, you get a number. From the cross product, you get a vector. In this case, if the angle is 90 degrees, we're measuring from that positive angle, sine of 90 is 1, you get all the torque. It's just R times F. If the angle were 0, sine of 0 is 0, you get no torque. You're pulling on that axis of rotation. You're not providing a torque about the axis. You're not tending to try to rotate the object or whatever, rotate something about that axis. Okay? And everything in between. If phi is negative, that's negative torque. That's a clockwise torque. If phi is positive, that's a counterclockwise torque, the way I've set up the coordinate system. And that's a positive torque. Okay. By the way, the units of torque are Newton meters. That is not energy. I know that energy has the same units, but this is not energy, this is torque. When I'm thinking about torque, I know that the units are Newton meters. I sometimes get confused. I'll think of that being a little X instead of a dot, meaning, hey, that's the cross product between a force and a position, but okay. It's context. You have to look at it in context, and if you're talking about torques, Newton meter is torque. Okay. How does this relate to rotations? Well, remember from Newton's second law, we all know this one by now, the net force was equal to ma. That's been drilled into our heads over and over again. For rotations, the second law for rotations force becomes torque, mass becomes moment of inertia, and acceleration becomes angular acceleration. I'm going to go ahead and give it a vector symbol. We'll deal with the vectors as they arise, okay? Angular acceleration, angular velocity, all those things are vectors. Okay. Moment of inertia, angular acceleration, torque. So I want to do a little simple example based on this idea. Let's say that you have a pulley that is suspended by its center, and so I'll put some little, it's suspended, I'll call that the normal force. It's hanging by its center, and it's got a very lightweight string wrapped around it, and here's a little hanging mass M. Okay? So what's going to happen? You release the mass, this is going to fall, and this is going to start to spin. Only now, unlike what we've been doing over and over again when we had these pulleys, now that pulley is not massless, frictionless magic, okay? It has some mass. Let's say it's a disc. So it's a regular pulley, it's a disc, and it has mass M and radius R. Okay? The string is coming off at such an angle that the angle between that force that's being applied to the pulley and, you know, I'm going to say it's perfectly tangential. So the angle here is actually -90. That's going to tend to cause, the way I've drawn it, that's going to tend to be a clockwise rotation. So this tension that's in the string is providing a positive torque, a negative torque. Clockwise is negative. Okay. So let me draw the free body diagram for the disc. Here's the disc. Normal force. Big mg. But there is also a tension that is acting on the pulley out here at this distance. That's a torque. Okay? This distance is R. All right? For the hanging mass, that's pretty simple. We've done this over and over again. There's the tension and mg. Okay? Now, I'm going to make up positive and down negative. That's going to work out nicely because it's really easy to get kind of messed up with the SIGNs on these torque problems and angular, or it is for me, angular acceleration and angular velocity. So that negative torque is going to cause a negative rotation here, and this mass is falling. So as it falls, that's a negative acceleration and a negative torque. Okay, I think it'll come out right. All right, so what I want to find is, remember it's a disc, I want to find the acceleration of the falling mass. Find A. Okay? So, you know, depending on the mass of, if this is a very small mass and this is a big massive pulley, it's going to fall very slowly, very slowly. If this is a big mass and a really lightweight pulley, it's going to fall really fast. So the first thing I'm going to do is set up the equations for the rotation. By the way, this force, big mg, and the normal force, they are not providing any torque on that pulley. They're acting about the center of the pulley. That's the axis of rotation. The radius at this point is 0. No torque between these two. This is fixed. It's hanging from something. It's not. There, you could do problems where this is falling and this is falling, but that's for another day. Okay? This is fixed. So the torque, the net torque, is equal to I alpha. What is the torque? Well, it's RT with a negative sign. Just like we did with Newton's second law for translation, okay, we make those forces positive and negative. We make in this case, we make the torques positive and negative. So you have a negative torque, RT, and that's equal to I alpha. This is a disk, so I is equal to mr squared over 2. I'm working this out where I can get to the point where I can solve for the acceleration, okay? So I'm going to plug this in. Negative RT, T stands for tension, not torque, is equal to mr squared over 2 alpha. That R cancels and that R cancels. So now I have a relationship between the tension and the angular acceleration. T, or negative T, is equal to mr over 2 alpha. Okay? For little m, I know I already erased it, but for little m, we have, remember, down was negative, up was positive, so T minus little mg is equal to little ma. That's easy enough, okay? So T is equal to mg plus ma. All right? Now, I have an expression for the torque, for the tension here. That's big M. Gonna plug that in here. And I get negative mr over 2 alpha is equal to mg plus ma. Here's the trick. If I can relate alpha to this tangential acceleration, right? Then I can solve for the acceleration. Because I don't have the picture anymore, but for a point on the edge of the disk, the acceleration is equal to, we talked about this the other day, the acceleration is equal to r alpha. If you're at a radius r and the object is accelerating at some angular acceleration alpha, then the tangential acceleration, which matches the acceleration of that falling object, is equal to r alpha. So I'm going to solve for alpha. Alpha is equal to A over R. And I'll use that here. So I'll plug this in here. You get minus mr over 2 times alpha, which is A over R, is equal to little mg plus little ma. I'm going to erase this. Okay? Look at this. It's independent of the radius. So you get minus ma over 2 is big Ma is equal to little mg plus little ma. Collect terms and solve. So A is equal to minus mg divided by big M, no, not big M, divided by little m plus big M over 2. That's it. That's the acceleration of the falling mass. It's negative, going down, and just like I said, if this mass is very large, then you get a small acceleration. If this mass is small and these masses are large, you get a fairly large acceleration, okay? What happens if this mass is 0? Like we had before with the frictionless magic pulley. Minus g. Yeah, it's falling. There's nothing stopping it. It's just free fall. Okay, I think we'll stop here.